on behalf of the research team here at UTT, we will be discussing the preliminary results of a study to measure and reduce atmospheric carbon dioxide emissions in Trinidad and Tobago's transport sector using mathematical modeling. So we know that traffic congestion affects all of us negatively as it lengthens our travel time and produces excess carbon dioxide emissions. And I'm certain most of you were stuck in traffic heading home to see this very presentation. That's another negative of traffic congestion, being stuck in traffic in hot sun. So our goal is to reduce traffic congestion and hence CO2 emissions. So from the statistics, we can see, in particular, the last 2 points, globally, the transport sector contributes 25% of CO2 emissions. And locally, here in Trinidad and Tobago, we have 17%. So we can see the need to reduce these emissions from traffic congestion. So before we go into our results, we must first understand that because of the insufficient data that were available to Trinidad and Tobago, we needed to use certain approximations and assumptions in order to obtain reasonable results from the literature that we considered. Also, the literature that we considered, they did not consider small population such as Trinidad and Tobago, since their smallest were around 5 billion people and 49 million vehicles. So now we will look at our first model, which deals with the governing equations for CO2 emissions. And this model was studied by Donald et al., for which we have made certain modifications and additions as well. So H stands for, or is defined as the human population of Trinidad and Tobago, including immigrants. C is defined as the carbon dioxide emissions, and V is defined as the vehicle population of Trinidad and Tobago, where this value was assumed since we do not have actual numbers for vehicles on our streets or the roadways. Now, if we take a look at the first equation, simply the change in humans over the change in time, it is related to the growth rate, R. Also, the human carrying capacity, how many humans a certain environment can hold, L. We also have this expression here, which stands for the death rate of humans due to carbon concentration. And we have this expression here, which we have added to Donald et al.'s model, which he did not consider. And this stands for the death rate of humans due to vehicular accidents. Next, if we look at the change in carbon over the change in time, we have C0, which represents the natural carbon dioxide emissions from plants and respiratory organisms. We also have the second expression, which stands for the carbon dioxide emissions from human activities. Also, we have gamma, which stands for the carbon dioxide emissions from vehicles. Lastly, we have the change in vehicles over the change in time, where the first parameter represents the number of humans that demand mobility. We also introduce the vehicle carrying capacity K. Again, this was not considered in his model. And lastly, we have the death rate of vehicles, vehicles being replaced. Additionally, his model considered CO2 emission from forest biomass. However, here in Trinidad and Tobago, the CO2 from the forest biomass was not sufficient when compared to the other sources of carbon dioxide emissions. Next, we have the governing equations for the SIRER model, or simply SIR model. And this model is used to study the traffic congestion section of our research. And this model was studied by Rafsanjani et al. So the SIR model simply stands for susceptible, infected, and recovered. And it is a model that is used to document the dynamics of biological diseases or viruses. However, over time, this model has been adapted to non-biological viruses. In this case, we treat traffic congestion as a form of a virus or infection. So we have S stands for, or is defined as the susceptible vehicles or cars entering roadways. We have I, which is the cars stuck in traffic congestion. RE means cars queuing at red lights, and R is equal to cars recovered from traffic congestion. Again, if we look at our first equation, we have alpha, which represents the birth rate. So that will be cars entering the road. Then we have, in particular, lambda, which represents the transmission of susceptible vehicles into congested vehicles. Also, if we take a look at the second equation, we would see that same expression showing up again. That is because all of these are connected. So they're like compartments and they're all connected. If we look at the third equation, we would see beta in particular, which represents the rate of vehicles queuing at red lights. So again, these models were coded into MATLAB and solved simultaneously in order to obtain different numerical examples that we would use to determine how traffic congestion can be reduced, as well as the carbon dioxide emissions. Also, for future study, we plan to combine these models to obtain more, we can say, more challenging results. So before looking at our results, in order to obtain a reasonable comparison between the different modes of transportation that we have here in Trinidad and Tobago for the public, we chose the Toyota Hiace as the 12-seater maxi taxis, the Mitsubishi Fuso Rosa as our 24-seater maxi taxis, and for the taxis and private vehicles, we assume them to have an average fuel capacity of 55 liters. This was assumed in this way in order to reduce the complexity of the calculations in order to obtain a result. But however, we can always increase the complexity bit by bit to introduce more models of taxis and private vehicles, as well as the maxi taxis as well. So here we simply have a simple flow diagram that shows the transition from susceptible vehicles becoming infected. Then infected, we move to, so say like you on a highway, and then you move into, main roads and you end up at a red light, and then eventually you would come out of traffic. Right? So again, this uses the SIR model, and we treat traffic congestion as our infection. And for this model, from the governing equation that we saw, we will look at two experiments, one which will be variant beta, and the second which will be variant lambda. So first we will look at variant beta on the transport sector for the different modes of transportation that we mentioned. And beta is defined as the rate of cars queuing at red lights. High beta is defined as low rate of cars queuing at red lights. So from our simulation from MATLAB, we were able to produce 4 graphs for each individual vehicle. So we first have on top the 12-seater, then followed by the 24, then taxis, and last we have private vehicles. And each graph is cars recovered from congestion against cars queuing at red lights. And so we can see that each figure shows the same pattern, and the blue curve represents a low beta, and the purple curve on top represents a high beta value. So the trajectory starts at this region here at this point, and it travels along this path until we can say this point here, which can represent peak hours, right? So, where we would have the most amount of traffic, and then it travels along this path until it slowly approaches zero. So this is the whole idea of the SIR model, having something that slowly dies out as time progresses. So from each of our graphs, we saw that for a high beta value, the number of cars queuing at red lights decreases, where the 24-seater showed the highest decrease. So effective traffic optimization and reduction policies are needed. So the high beta in the real world can represent the following. So we have adaptive traffic signal control, which goes together with the AI and machine learning based optimization. And this simply uses sensors and AI technology that study traffic conditions in real time and adjust accordingly so that we can reduce travel time and the building up of vehicles at red lights. So for example, this is used in Los Angeles, and they have reduced travel time by 12% and intersection delays by 32%. Next, we have green wave coordination, which is used in New York City, for example. And this is simply where the traffic lights are timed so that drivers traveling at certain speed would hit green lights. So again, minimizing stops. And this is mostly used for the buses. And lastly, we have traffic signal priority and time of the signal plans, which again is more for the buses. Right. So next, we will look at our second experiment, which deals with variant lambda. And lambda is defined as the transmission rate of susceptible vehicles to congested vehicles. High lambda is equal to high rate of transmission. So again, from our simulation, we were able to produce numerical examples for each mode of transportation. So the trajectory starts at this region and it travels along this pathway until it slowly approaches zero. So again, this is showing that the traffic is dying out as time progresses. So our goal is to see how much it reduces and how quickly we can reduce these congestion. So each graph represents congested vehicles against susceptible vehicles. So the blue curve represents a low lambda, where the purple curve represents a high lambda. And from each of our graphs, we saw that for a low lambda, we reduce the number of vehicles becoming congested in traffic. Again, with the 24 seater showing the highest decrease in that effect. So policies that reduce the number of vehicles becoming congested in traffic are needed. So this low lambda can represent improved public transportation. So countries in the Caribbean, such as Jamaica and Barbados, have implemented improved public transportation, that is, making it more accessible, more affordable, and more reliable to the public. We also have carpooling and high occupancy vehicle lanes. Again, this reduces the number of vehicles on the streets. We previously saw traffic signal optimization, one of my favorites. The promotion of active transport, where countries in Asia, they have dedicated tunnels only for walking and cycling. And lastly, flexible working hours. So we can change or adjust working hours so that we can reduce the number of vehicles during peak working times. So now that we have seen the traffic congestion section, we will now look at the carbon dioxide emissions and the human capacity for those same modes of transport for our public transportation. So here, we simply have a graph that shows private vehicles being the first line. The second line represents taxis. The third represents 12-seater maxi taxis. And last, we have 24-seater maxi taxis. So here we simply chose a population of around 200,000 people. And we investigated how many vehicles we would need to accommodate that number of people. So in doing that, we assume that the private vehicles can hold 2 people, the taxis can hold 5, and both maxi taxis at full capacity. So in order to accommodate 200,000 people, we would need approximately 100,000 private vehicles, or instead, we can use approximately 9,000 24-seater. So we can see the significant decrease in the number of vehicles that we would have or need to accommodate that number of people. Next, we have the carbon dioxide comparison between the 12-seater, which is the blue line, the blue curve, sorry, and the 24-seater, the red curve. And we can see that the 24-seater produces more CO2 emissions in tons than the 12-seater. And this is due to the model that we chose. And that model has a lower fuel efficiency and a higher fuel consumption than the Toyota Hiace for the 12-seater. However, we can always consider more fuel-efficient 24-seater buses or maxi taxis. Next, we have the comparison of the taxis, the blue line, blue curve, together with both maxi taxis. And we can clearly see that the taxis produces far more carbon dioxide emissions than both maxi taxis. So from an article in Trinidad and Tobago in 2021, their statistics showed that we have approximately 6,700 total buses or maxi taxis. However, they did not specify which were 12 and 24. So from our personal observation, we assume 40% were 12, 60% were 24. And from simple calculations, this number of 12-seater can hold approximately 32,000 people. This number of 24-seater can approximately hold 97,000 people. So for a very small population, right, or, in Trinidad and Tobago, so a fraction of our population. So this range here, we would require approximately 8 to 9,000 24-seater or 17,000 12-seater maxi taxis. On the other hand, if we were to consider taxis and private vehicles for that same population range, we would require 40 to 42,000 taxis or 100 to 103,000 private vehicles. So we can see the significant increase in the number of vehicles that we would require. Or simply, instead, we can use or acquire around 8 to 9,000 24-seater maxi taxis, thereby again reducing the number of vehicles on our streets. So one may wonder, since the 12-seater has a better or more fuel efficient than the 24-seater, we can maybe acquire more acquire the 12-seater instead. However, in doing that, we would have more 12-seater since the number there is double. And doing that, we would increase the number of vehicles, and that will lead to an increase in traffic, which will increase CO2 emissions. So in order to obtain a perfect balance between the traffic congestion and carbon dioxide emissions, we can look at more fuel efficient 24-seater. And for future study, we can also look at the larger buses as well, the PTSC buses. So from our results, we have mathematically demonstrated the effects of traffic policies on emissions. The policies can be enacted to reduce traffic and decrease emissions. We saw that high beta values decrease the number of vehicles queuing at red lights. So that represents effective and efficient traffic light system. We saw that low lambda values decrease the rate of susceptible vehicles becoming congested in traffic. And the implementation of additional fuel-efficient maxi taxis or buses for public transportation decrease traffic congestion and CO2 emissions. So before I close, I would like to thank our funders, which is the project, which is facilitated under the HIT Reset, funded via the Organization of African, Caribbean, and Pacific States as a part of the ACP Innovation Fund, sponsored by the 11th European Union Development Fund. So thank you for listening, and here are my references. Any questions? So now open to any questions.
Thank you for presenting our initial results, Hassan. Um, so, well, the audience, you would have just seen the results of that, like I said, our preliminary work, which we hope to expand quickly
Right.
and soon, right? So that with this preliminary work that has demonstrated results that we expected, now when we add the complexity, we can trust the results
Yes.
that we would get. So please, we would appreciate your constructive feedback and any questions at this time.
Okay, Perry Pola. I'm with the Hitterset Caribbean program. I thoroughly enjoyed your presentation. I thought it was a very interesting and the parameters that you chose.
Yeah.
I have two questions. The first one, basically, relates to, do you think that the TT WeSafe app that
Mm-hmm.
is being developed will be able to supply all the data you need for your the parameters in your equation, or do you need
Right.
supplementary
So
information? I'll leave it at that first question.
yeah. So I think as of right now, the app doesn't have that like implemented into the app, so it could like record the CO2 emissions or stuff like that, so we can use actual data that we have. But I think it is being done. It was discussed, um, where we can use that app to like track travel times. So we can use, simple CO2 emissions equations where we can use distance travel to calculate the amount of CO2 that a vehicle would emit, and we can use that data into our model. So we can, instead of using assumptions and approximations, we would have that data there to use.
Well, that actually leads me into my second question,
Mhm,
which is it's not related to the equation that you showed, but just for something for consideration.
mhm,
My question was whether or not fuel sales, I think Heritage
mhm,
Petroleum, I'm getting the company name wrong, supplies us with petroleum.
mhm,
So therefore, it may be possible to get data on the
mhm,
types of fuel being sold to gas stations. Could
mhm.
that be a proxy user to calculate potential CO2 emissions? Could it be used as a proxy?
Um, well, that's basically what I did with the calculation for the to get the um, amount of CO2 in tons. So basically, what I did, I had a table that had well, they just use gasoline, diesel, and they also had CNG. And basically, what they would have is the emission factor, and you basically use that times the amount of fuel that the car can hold, and basically from that you can get the CO2 emissions. Yeah, but that would be like for the whole tank. It would not be like if you travel from, let's say, a certain distance, so it would not give you that like if you want maybe like a 5 kilometer or something, it might be difficult to do that.
The
Yeah.
other thing that the app allows us to do is if we know um sorry to jump in, Hassan. Let me
Yeah,
just
yeah,
add to this. Because we'll be able to see the people who are using it, let's
yeah,
say, well, they're taxi drivers, so they'll be doing the same route. So that allows us to track the difference in times that the same route is taking at different times as well, which will also help us with our congestion and our red light modeling as well, right?
yeah.
So, and then of course, at some point we'd like to put in, a variety of vehicles that are using a variety of different types of fuels. But again, for our initial model, we didn't do that. We chose to go as simple as possible for the first iteration, I should say.
Yeah.
Hi, good evening. My name is Wendy. Thank you so much for your presentation. It was really very interesting. So I guess Dr. John, as you were saying, in the future reiterations of your of the model, you would include like the impacts of having policies like for electric vehicles and
Yeah.
or electric buses and those
Yeah.
kinds of
Yeah, we
things.
would like to. And also, this one, we don't have we didn't well not we don't have as yet like numbers in terms of significant users for CNG, and now we have the propane
Yeah.
vehicles as well. And we would like to be able to add those in, in the future as well.
Okay, thank you.
Thank you.
Okay, I'll take the opportunity to ask another question. Now that well, let's say the app is up and running, and you're using the data to do your calculations, your mathematical modeling. How then can we be beyond just publishing a paper? How can we use the data that you have generated to influence transportation in policy in Trinidad and Tobago? Have you established a plan to do so?
Um, I don't, well,
Right. Let me answer this one, please.
okay.
Yeah. So we see that you'd have seen in Hassan's presentation that we have policies that we know would represent some of the things that we're saying need to be done. So yes, so our hope is that we continue to make these recommendations, and we will have the data that demonstrates that if you do this, then here's the quantitative reduction you can expect. And then we are actually hoping to get a couple of at least even like city corporations to work with us to try some of these recommendations and see how they work. So for example, we are myself and Hassan, we are mainly located at the Point Lisa's campus for UTT. So Hassan's been taking measurements of traffic here in Point Lisa's, right? So our hope is once we have enough data, and then once we have some recommendations, we can at least see if we can get some buy-in from, from some of the municipal corporations to try a couple of these strategies, and let's see if what our model suggests would happen does happen. And of course, if we can get it to happen on a small scale, then it'll be easier to convince people to try it on a larger scale. So we'd have that as a long-term plan. But we don't want this work to just be academic. We do see a need for it. There's too much traffic, there are too many vehicles, and there's too much CO2. And of course, other
Yeah.
emissions that occur with, too many cars being on the road. I hope I answered your question.
Yes, you did.
Great. Are there any additional questions or comments for this work?
No, just a comment from me. Thank you so much, Dr. John and Hassan, and I appreciate that you tried to simplify it for us. Thanks.
Yes.
All right. Well, there doesn't seem to be any other questions or comments, but if you think of anything later, you'll see my email address and Dr. Chedi's email address. Yes, you can always drop us an email, and we will try to address those. Or if you have any suggestions, we'll be glad. If you want to work with us, if you have data that we could use, we will be glad for that as well. And just again, on behalf of the entire team, thank you so much for your attention and your enthusiasm about this work. Have a great long weekend.
You too. Thank you very much.
Thanks. Bye.
Bye.
Bye.